Getting the best from Chemistry Explained needs you to participate. So write notes, complete tasks on paper or tablet. Pause and control the pace at which the lesson goes. Crucially, complete the tasks when prompted. That means pausing the lesson, taking your time, thinking the problem through. Only when you're ready, continue. Correct your work before moving on to the next slide. Electron structure. You will have met in your pre-A-level chemistry the idea of there being a maximum numbers of electrons in any particular shell. Now those numbers that you've met were a simplification, and at A-level you will use the idea from quantum mechanics that the maxima are obtained from the formula 2n squared, where n is the number or the electron shell number. So looking at this table, we've got a shell number n. The electron maxima is maximum for that is 2n squared. So could you pause the video and write in the maximum numbers of electrons for each shell using 2n squared. Come back, resume the lesson when you have done that. Okay, so let me do that as well. So we're going to go 2 times 1 squared. So that is 2. So there's a maximum of 2 electrons in the first shell. We've got 2 times 2 squared. 2 squared is 4, so that is 8. So the maximum in the second shell is 8. 2 times 3 squared, well 3 squared is 9, so the maximum in the third shell is 18. And 2 times 4 squared, well 4 squared is 16, so the maximum in the fourth shell is 32. So these are the maximum numbers of electrons in first, second, third and fourth shell that you will be working with at A-level. A second new idea at A-level about electrons is the idea of the atomic orbitals. So these are three-dimensional regions around the nucleus. Three-dimensional regions. And they hold up to 2 electrons. And those electrons must have opposite spins. There are 2 orbitals that you need to know the shapes of. So the 2 regions of space, 3-dimensional regions of space that surround the nucleus, called s and p orbitals, that you need to know the shape of. The s orbital is spherical, and the region of space is actually the surface. It's like the peel of an orange. It's the surface of the sphere, not the core or the center. So the surface of the sphere is the s orbital. P orbitals, known as dumbbell shaped or double lobes, 2 lobes either side of the plane of the nucleus. Now these are actually regions, solid regions, so anywhere within that lobe is the region of space. So the p orbital is 2 solid lobes. The s orbital is the surface of a sphere. Okay, they are both center of the nucleus. In pre-A-level chemistry, you thought of electrons being only in shells. But at A-level, we have to think of the shells themselves being composed of subshells. And those subshells contain a particular type of orbital. The numbers of subshells is equal to the principal shell number. So, if we look here, shell number 1 has 1 subshell. That type of subshell is an S subshell, and the shell maximum is 2. So we know that, if you remember, we calculated the shell maxima on a previous slide. So the maximum for the first shell is 2. The numbers of subshells is equal, the subshells is equal to the shell number, and I'm telling you that that type of subshell is an S subshell. So if we look at shell number 2, could you fill in the numbers of subshells and the shell maxima, and so on for 3 and for 4. So I'll pause the lesson and fill in the number of subshells and the shell maxima from your recollection of the previous slide. Do that now. Resume when you are ready. Okay, so if the shell number is 2, well, we are told from quantum mechanics that the numbers of subshells is 2. And we know that the shell maximum for the second shell is 8. We calculated that on a previous slide. I will tell you that the two types of subshell are S and P. Moving on to shell number 3, well, there are 3 subshells. The maximum numbers of electrons in the third shell is 18. The S and P are present as subshells, but we have a third subshell, a D subshell. Then the fourth shell has 4 subshells. We know that it's got 32 as a maximum, so it's S, P, D, and F. Now, from that information, you should be able to calculate the numbers of electrons that are allowed in each subshell type. Comparing the first shell to the second shell, the type of subshell and the shell maximums, should be able to work out the numbers of electrons allowed, maximum numbers of electrons allowed in each subshell type. Could you pause the video and attempt that deduction? Come back when you are ready. Okay, so the difference between, I'll just remove my working here. The difference between the first shell and the second shell is 6 electrons, and that is due to a p orbital. So a p has a maximum of 6 electrons. We know there's a maximum of 2 in the S because the first shell has a maximum of 2 and only consists of an S subshell. So the S subshell must have a maximum of 2. Moving from the first to the second, we go from 2 to 8, so the P subshell must have a maximum of 6 electrons. And if we compare the second to the third, well, there's a difference of 10, which must be due to the D subshell. So our maxima are S 2 electrons, P 6 electrons, and D 10 electrons. Now we also need to consider atomic orbitals. A rule of quantum mechanics is that there are a maximum of 2 electrons per orbital. So if the S subshell has a maximum of 2, what's the number of orbitals present? Obviously it is 1. Could you work out the other numbers of orbitals for P subshells and D subshells? Pause the video and do that now. Okay, so if we've got a maximum of 6 electrons in a P subshell, then that must contain 3 orbitals. There's 2 electrons maximum per orbital. So if we've got a maximum of 6, we must have 3 orbitals present. D subshell, there's a maximum of 10 electrons, so that means there must be 5 orbitals. So within an S subshell there's 1 orbital, within a P subshell there's 3 orbitals, within a D subshell there's 5 orbitals. So let's just tidy that up for you. Just to return to P, the P subshell, we drew, or I showed you a drawing of a P orbital earlier, but we've deduced from the numbers of electrons that there are 3 P orbitals within a P subshell. And those are orientated along the 3 dimension axes. So we've got Px, this would be Px, this would be Pz. Could you pause the video and draw the Py orbital? Okay, so the Py orbital, very simple, is orientated along the y-axis. So we've got Px, Pz and Py. 3 P orbital has a maximum of 2 electrons. The P subshell has a maximum of 6 electrons because it's got 3 orbitals in it. So we need to just to recap and summarize A-level electron theory. For example, we need to look at the shell number, what that is, what the shell consists of, and relate that to orbitals and the shell maxima. So, an S subshell, if I just highlight this, and in shell number 1 consists of an S subshell, lunch, with 1 S orbital, and we label that 1s. So shell number 1 consists of an S subshell. An S subshell just has 1 S orbital, which was spherical if you remember, and we label that subshell 1s. What can we see? S subshell. The S subshell holds up to 2 electrons, so the shell maximum for the first shell is 2. Could you complete a similar summary for shell number 2? Pause the video. When you've done that, resume the lesson. Okay, so we know that the second shell consists of 2 subshells, an S subshell and a P subshell. So the second shell consists of 2 subshells, an S subshell and a P subshell. And we label the S subshell of the second shell 2S, and we label the P subshell of the second shell 2P. But recall that the P subshell consists of 3 orbitals. So the S subshell holds up to 2 electrons. The P subshell, because it's got 3 orbitals, will hold up to 6. So the maximum numbers of electrons in the second shell is 8. Consists of an S subshell and a P subshell with their own maximums of 2 and 6. Could you write a similar summary for shell number 3? Okay, so let's go on from there. The third shell contains 3 subshells, an S subshell, which we label 3s, a P subshell we label 3p, and a D subshell we label 3d. The 3s subshell has 1 orbital, the 3p has 3 orbitals, and the 3d has 5 orbitals. So I haven't mentioned that before, but the D subshell is composed of 5 orbitals. Yes, we did mention it earlier. So 5 orbitals in the 3d subshell. So what does that mean in terms of numbers of electrons? Well, an S subshell can hold up to 2 electrons. The P subshell, got 3 orbitals, can hold up to 6, and the D subshell can hold up to 10, which means the maximum numbers of electrons in the third shell is 18. So before you move on, you may need to recap on this part of the lesson. This cannot be ignored, it must be known. So let's discuss the order of filling of the orbitals and subshells. The lowest energy subshells are filled first. So we need to have an order for the energy of the subshells. And not surprisingly, the lowest energy subshell is 1s, then 2s followed by 2p, so the second shell is split into 2s and 2p. Then the third shell is split into 3s, which is of lower energy than 3p, which is lower energy than 3d. But 4s comes between 3p and 3d, so 4s is of lower energy than 3d. Then the progression 4p and so on. So the order of filling is identical. If we fill the lowest subshells first, we'll fill the first 1s, the 2s, 2p, 3s, 3p, 4s comes before 3d, 4p, 5s, 4d comes before 5p, etc. So let's do some problems writing electron configurations in terms of subshells. So if I model the first one, which is sodium, well, sodium has got 11 electrons. So I write the lowest energy subshell, 1s, and I put 2 electrons in that. That's the capacity for an S subshell. The next lowest energy subshell is 2s, also has room for 2 electrons. The next lowest energy subshell is 2p, which has a capacity of 6. I've got 1 electron left to place into a subshell. The next lowest energy subshell is 3s, which I've placed that 1 electron. So there we have the electron subshell configuration for sodium. Now, I'd like you to try to write the electron configuration in terms of subshells for magnesium. Try that one, we'll go through it, and then you can attempt the others. So pause the video and write the subshell configuration for magnesium. Okay, so revealing the order of filling, and here is the subshell configuration for magnesium. Very simple. Of 1s, 2s, 2p, 3s, 1s2, 2s2, 2p6, and 3s2. So there is the electron configuration for magnesium in terms of subshells. Complete the remaining 4. Refer to this aide-memoire for the order of filling of the subshells at the top of the page. Pause, complete, and resume the lesson. Okay, so let's just reveal for helium. Very simple. I hope I didn't fool anyone. 2 electrons goes into the lowest energy subshell, which is 1s, so 1s2. Iron, 1s2, 2s2, 2p6, 3s2, 3p6. We fill 4s before 3d, so 4s is filled before 3d. we've got 6 electrons left over to place into the 3D subshell, which I might remind you has a capacity of 10. So all the subshells are filled up to 4s2, and then the 6 remaining electrons go into the 3D subshell, which is partially filled. So let's move on to bromine. If you need to do corrections or for bromine on nitrogen, pause the video and do them. But here is the answer for bromine. We fill the subshells in order: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 before 3D, 3d10. We've got 5 electrons remaining and they go into the 4p. So after 3D, if we look at the order at the top of the page, 3D is followed by 4p. And then, excuse that scribble, if we reveal nitrogen, 1s2, 2s2, 2p3. Okay, let's move on. Now, the periodic table reflects the order of subshell filling. So we can use the periodic table to recall or to remind us on the order of subshell filling. So there is the order of subshell filling. And you will see 1s, we know there's 2 electrons. Well, in the first period, look, there's 1, 2 elements, so 1s2. Then we go on to the second period for element number 3, and there's a group of 2 elements, 3 and 4. So electrons 3 and 4 go into 2s. Then on the second period there's a group of 6. Well, so elements 5 to 10 go in that part of the period, second block of 6. Well, electrons 5 to 10 go into 2p. Then we go back to the third period. So element 11 goes in the third period. Well, electron 11 goes into the third shell. In fact, 11 and 12 go into a little group of their own, 3s. Then we move over again to a group of 6. 3p. So the third period is split into a group of 2 and a group of 6. Well, the third shell starts off as a group of 2 electrons and a group of 6 electrons. 2 electrons in the 3s subshell, 6 electrons in the 3p subshell. Then we go in the periodic table, element 19, we go back to the fourth period. So 19 and 20, well, electrons 19 and 20 go into 4s. Well, this is 2s, this is 3s, this is 4s filling equivalent to. Then we've got a set of 10 elements. Well, that corresponds to filling 3D. Okay, so that's got 10 elements, 10 electrons. Is an exact reflection of the filling of the subshells in the ordering of the periodic table. Then, after we've filled 3D with 10 electrons, after we've put in 10 elements into the third period between calcium, after calcium, then we're into a set of 6. We're back into 4p. So, guess what comes after 4p? 5s. Then 4d, 5p, etc. But as far as A-level is concerned, you only need to know the filling up to that point. But the periodic table will reflect future subshell energy levels, future order of filling of the subshells. So, the periodic table reflects exactly the order of filling of the subshells. So that is your aid memoir. Now, along exactly the same lines, we write electron configurations in subshells for ions. So let's take a lithium ion. Well, we've got an atomic number of 3, but it's a +1 ion. So 3 electrons minus 1. We only have to find the configuration involving 2 electrons for lithium. So that's easy enough. It's 1s2. The lowest energy subshell, 1s, is 2 electrons. So if we look at calcium, just point out we've got 20 electrons in the atom, but it's lost 2 electrons in the ion. So could you write the electron configuration for calcium, oxygen, the oxide ion, the bromide ion, the nitride ion? Write them, pause the video, think them through carefully, write them down, and restart the lesson when you want to check your answers. Okay, so here are the answers. So calcium only got 18 electrons to accommodate. So 1s2, 2s2, 2p6, 3s2, 3p6 comes to 18. The oxide ion has got 2 additional electrons. So we've got to accommodate 10 electrons. So this is oxide ion, 8 for the atomic number, plus 2, it's a 2- ion, so we've got 10 electrons to accommodate. 1s2, 2s2, 2p6. The bromide ion, 36 electrons to accommodate. Check your answer against that, make sure you've got the order of filling correct. And the nitride ion has got 3 additional electrons, again making 10. So check your answers there, please, before moving on. Okay, so having looked at electron configurations in terms of subshells, we have also discussed the fact that the subshells are themselves composed of orbitals. So it is useful in some more advanced chemistry to write electron configurations with electrons placed in orbitals. Now to do that, we use the electrons in boxes notation. So I'll just show you what it looks like for lithium. Lithium, 1s2, 2s1. So an s subshell has 1 orbital, so we simply have 1 box, but 2 electrons within it. The 2s subshell, well, it's an s subshell, so it has 1 orbital, so that's 1 box. But you'll notice that I represented the electrons as a half arrow, and they are pointing in opposite directions. You may recall from an earlier slide that whilst it is possible to have 2 electrons in 1 orbital, those electrons must be of opposite spin. So we indicate that by representing an electron as a half arrow pointing up or pointing down. So when you pair them up, they must be of opposite spins. So let me give you a problem. Can you write the electron configuration for fluorine, which in subshells is 1s2, 2s2, 2p5? Can you write that in electrons in boxes notation? Pause the video, do your best. Okay, so it looks like this. 1s2, well, an s subshell has 1 orbital. 2s, an s subshell has 1 orbital, but a p subshell has 3 orbitals, but they are all of the same energy, so we join the 3 boxes together. So each box represents an orbital, px, py, pz, if you recall, and we place 5 electrons, so we've got to pair electrons twice, so they must be of opposite spins, and then 1 electron singly. Now normally that is normally presented with an arrow, half arrow pointing upwards. It can be up or down. you'll normally see them with the arrow pointing upwards. For some reason, I have it pointing downwards. So, have a look at the next problem. Phosphorus. Now, there's a couple of issues that arise with phosphorus, but if you make an attempt to draw the electrons in boxes notation configuration for phosphorus, attempt that and then come back and view the answer when you are ready. Okay, so the electrons in boxes notation gives us these boxes. 1s2, no problem. 2s2 as per expected. 2p6, well, we've got 3p orbitals, so 3 boxes at the same energy, so joined together and filled. 3s, 2 electrons, but 3p has got 3 electrons in it. We still draw 3 orbitals, so we've still got our 3 orbitals for the p subshell, but the orbitals are occupied singly. Before pairing. So where possible, the electrons will spread out to minimize electron-electron repulsions. By pairing electrons, for instance 3s2, you've got 2 electrons within the same region of space, so there's increased, or there are, electron-electron repulsions being produced there. To minimize those electron-electron repulsions, the electrons occupy the orbitals singly before pairing. So let's do some sort of review problems before we charge off and say, okay, we've got electron structure under control. So I'm going to say to you, looking at sodium, it should be hopefully familiar to you. Give me the shell electron configuration, the subshell electron configuration, and then as orbitals. Pause the video, complete those 3 tasks, check your answers when you are ready. Okay, so the answer to the shell is obviously 281. The subshell 1s2, 2s2, 2p6, 3s1. And orbitals, single box, triple box, and single box occupied singly. So that's the electrons in boxes notation at the bottom. Okay, so I'm going to move on to problem number 2. So this is for sulfur with 16 electrons. Pause the video and give me, or write yourself, a shell, a subshell, and an orbital notation electron configuration for sulfur, please. Check your answers when you're ready. So here are the correct answers. 286 is electrons in shells. In subshells, 1s2, 2s2, 2p6, 3s2, 3p4. Please make sure that you are getting the notation correct here, and that you are writing the numbers of electrons as a superscript. Okay, so the numbers of electrons must be written as a, and then the orbital arrangement, like so, and then pair up. So 4 electrons in the 3p subshell for sulfur, 1 electron in the px, 1 in py, 1 in pz, and then you've got a 4th you need to pair up. If you're ready, I'm going to move on to problem 3. So for manganese, 25 electrons. Give me the shell, the subshell, and electrons in boxes notation. Pause the video, think it through, check your answers when you're ready. Okay, so I'm assuming you've got our answers here. Sorry, there was a little bit of a delay. 2,8,13,2. Now you may not be entirely happy with that, but I'll show how that 13 arises. Remember, we fill 4s before filling 3d. So it's 2,8,13,2 is the shell notation for manganese. Easier to write the subshell, 1s2, 2s2, 2p6, 3s2, 3p6, 4s before 3d. So 4s gets filled before 3d, and then these are in the third shell. So the total in the third shell are 2, and 6 makes 8, and 5 makes 13, which accounts for the 13 here. Now, in notation, electrons in boxes, we fill the orbitals as per standard up to 4s2, and then we've got 3d5. Well, the d, there is no pairing with only 5d subshell. Okay, so hopefully we've had an introduction to electron structure. You may want to repeat the lesson. You're welcome to do that. So for my final slide, just the obvious statement that to consolidate you need to practice, you need to find problems from whatever source you have available to you, but those sources which have comprehensive answers are the best. So attempt the problems, check your answers, move on when you are being consistently accurate and complete in your answers. Choose the next topic that you think for you is the one you need to focus on.